Alright, welcome back guys. So in this video here we're going to go over implicit differentiation. So let's start with just reviewing what we've done so far as far as differentiation goes. So if we have a function that is in this form here, right? So if it's y equal x, y in terms of x, we say that this is an explicit form, meaning y expressed in terms of x, right? Or we solve for y by itself and x on the other side, and we learn to how to differentiate this by using the power rule. So we get negative 6x. So that's the answer. So now we suppose we rewrite this as, so now let's take this form and rewrite that as where both of the variable on one side. So let's say we have 3x squared plus y minus 2, right? So that is the same form as, that is the same equation as the given one, and we call this one here is implicit. So this is where, you know, both variables one side and it's not in y form. So mainly, you know, it's not, you know, in y form, meaning y is not isolated. Okay, and in this section, when we use implicit differentiation, we are applying this technique to find derivative of functions where these functions cannot be, you know, solved for y in this form here. And usually those equations are not functions themselves. Let me correct myself. So there's going to be a lot of complicated equation where you can't isolate y by itself, meaning that those equations are not functions themselves. So when we ask to find derivative, it's more difficult to solve for y, and I'll give you example here. So, you know, example of but difficult to solve for explicitly will be something like this. When you have, let's say you have y, you know, times e to the x plus, you know, y squared natural log of y here as well equal to 7, or something like this here. It's not easy to solve for y because you have y in the front and we also have y as an argument, so it's hard to solve for y. Tensor is not a function, so how do we differentiate this? How do we find y prime without, you know, getting to explicit form like this here? Well, we're going to use the implicit differentiation to do that. So let's go back to this example here. So we said, you know, we find y prime by using different implicit differentiation. Okay, so let me show you a quick example. How do we do that for this easy example here? So if we have 3x squared plus y equal to 0. So when we find y prime, so we say find y prime or dy dx. Okay, so when we differentiate this implicitly, meaning we're going to go through the entire equation, we're going to differentiate each term with respect to x. Okay, so we're going to say d dx of each term. Okay. Well, d dx, or the derivative of 3x squared with respect to x, that's just going to be 6x. D dx of y, well, the derivative of y with respect to x is going to be dy dx. So in this case here, we're just going to do dy dx. Okay. Well, because y is dependent on x. So derivative of y with respect to x is going to be dy over dx. Here it's going to be 0 equals 0. And then we can change the dy dx as y prime because that's just the notation definition there. So now our y prime is negative 6x. So you can see we got the same answer using implicit differentiation as what we did without using implicit differentiation. So it's a little more confusing because, you know, all of a sudden we've been doing this explicitly every single time. Now we do implicit differentiation. So the notation becomes more critical when we find the derivative. So you want to pay attention to the notation themselves. Let's practice the next example here. So this one here is 3x squared minus y squared minus 2 equals 0. If we were asked to find the derivative using explicit approach, now notice that if I was to solve for y here, then I do this first, and then I divide by the negative, and then I would take the square root. But with the square root, we have a plus or minus situation. So this is the explicit form. So when we find y prime, we're going to have a plus or minus, you know, 2 possible answers. So it's a little more complicated. But even this one here, this is more complicated because this one is almost impossible to solve for y. So some of these equations are not easy to find y to solve it explicitly. So we have to use implicit differentiation. So this is how we're gonna do it. So we don't want to do this here. So when we differentiate this here with respect to y with respect to x, or y, find y prime. Anytime you have a y variable, remember, so this means some note, okay, finding y prime or dy dx means y depends on x. So anytime we differentiate the y with respect to x, there's a chain rule that apply where the y is the y variable is dependent on x, so we have to apply that part. So let's go ahead and do this. So d dx of each term, okay, d dx of y squared, d dx of 2. Okay. Well, this one is going to be easy. That's going to be 0. The first term is also easy as well. That's just 6x. Okay. All right. When we get to the y squared term, okay. So if we take the derivative of y squared with respect to x, so the chain roots start coming in. The outside function is the squared function. So we apply 2 times y as the derivative of the outside function. So the chain will say, okay, now since y is dependent on x, y is a function of x, we have to times it by the derivative of the inside function, inside function. And the derivative of the inside function is the y dependent on x. Here is going to be 0. Then the next line, we have 6x minus, well, 2y times, still say the same, the derivative of y with respect to x, whatever that is, okay, it's going to be dx dy right here. Excuse me, dy dx, sorry. All right, so this here is all y prime, okay? Like up here, when we do the derivative of y here, right? Essentially, you know, if we do the dx of y, that's dy over dx there, and that essentially your y prime. So in this case, we'll just reposition the dy dx with the y prime itself. 0. So now 6x minus 2y times y prime, dy dx is y prime. So now we can say, all right, y prime now is equal to negative 6x over negative 2y, y prime equal to 3x over y. Okay, so that is the derivative functions. So because these equations where you can't explicitly solve for y, not can, but it's hard to explicitly solve for y, the derivative equation will contain a variable y there and x as well. So up to this point, we only have the derivative function only expressed solely in just one variable x. Now you're going to start seeing the derivative functions depends on both variable x and y itself. Hence, when it's asked us to evaluate the derivative at 3, 5, we say that, okay, well, y prime at 3, 5 is 3 times 3 over 5. We just plug in whatever y and x we asked to evaluate. So that's 9/5. Okay. Right. So this graph here, this is an ellipse, or no, this is hyperbola. Let me just graph this really quick here and see what that looked like. So whatever that graph looked like, this is a hyperbola. So on this graph of hyperbola here, what we just found there is the tangent slope at the position 3, 5 is 9/5. Okay, but we can go over that more later. I just want to make sure that we understand the algebra part here. Let's do another example. This one is a little more confusing, okay, because we have a multiplication here, right? So the y is a function of x when we ask to find y prime or dy dx, okay? So if we have the variable times another variable, in this case, x and y are kind of separate functions here. So when we find the derivative of this, or dy, excuse me, ddx of this x times y here, we have to use the product rule, because you have a product of two functions, x is a function of cell, y is a function of cell, or y is a function of x. So when we do this here, we use the product rule. Use product rule. So now we have derivative of x is going to be 1 times y plus x times the derivative of y is going to be y prime there. So this is 0. So y plus x times dy dx is going to be y prime equals 0. So x y prime equals negative y. Therefore, y prime is equal to negative y over x. Okay. And we can evaluate this at negative 1, 2. So that's negative 2 over negative 1, which is going to be 2. Okay. So with the equation, or with the problem that involve a product rule within the the implicit differentiations there, it's a little more confusing because you have to apply the first basic rule first before you get to the the implicit differentiations, or as part of it when you get to y prime here. So the only time you put down y prime is when you are differentiating the variable y, because the variable y depends on x. Let's do an example. This one is more hectic here. All right, so as you can see, if we were to try and solve for y, how are we supposed to isolate this y here? We have 6y, and then we have the y as being part of the natural log as an input. So there's no way we can extract out that y without having both sides contain the variable y. So it's not easy in this case here. So we want to just go ahead and just implicitly differentiate this. We're going to go through, we're going to say, okay, let's find the ddx of each term here. So remember, this means find dy dx, or y is a function of x, meaning, make sure we times by y prime every time we differentiate a term, a variable y. Okay. All right, so let's do this. So derivative of x times natural of y. So this result us using a product rule. Okay, and then this is just power rule here, and then same thing here, power rule. Okay, so let's do it. So derivative of x times natural of y, that is, so that's u prime v plus v prime u, right? Remember that? So we have derivative of x in this case. So we can, I'm gonna write this as one time only, and then after that we're gonna see, I'm just gonna write out just the step to explain how to use a product rule here. So this is d dx of x times natural log of y, that's all u prime times v there, plus x times dx of natural log of y. So that's the product rule there, right? And then over here we have 6 times, since y is a function of x, so 6 times dx of y, so that's going to become y prime there, equal, this is going to be 9x squared. Okay. So let's finish the problem here. We have derivative of x is going to be 1 times natural log of y plus x times derivative of y is going to be, derivative of natural log of y is going to be 1 over y, but then y is a function of x, so we have to times by y prime, plus 6 times dy dx is y prime here, equal to 18x. Nope, no, we already took the derivative, so that's just going to be 9x squared. So now we have this y prime, that y prime to combine, so we have to solve for y prime here. We have to isolate it. So I'm going to go ahead and just factor out y prime. So we have y prime x over y plus 6, and then subtract this to the other side. So we have 9x squared, 9x squared minus natural log of y, and then we can divide both sides by x over y plus 6. We don't usually leave things as complex fractions, so we want times y over y to get rid of the fraction in the denominator. So we have 9x squared y minus y natural of y over x plus 6y. Okay, so this one is a little more work than the other questions.